so we're doing the Unit 8 review. So first question that we got is, says use the table and technology to find each model. So we have to find a linear model and we have to find a quadratic model. So what I'm going to do is I'm going to put all these numbers into a data table. So I'm going to bring up Desmos. I'm going to get a table with the plus sign, then hit table, and double check what my X values are. We got 1, 3, 4, 6, 7. So not exactly in order, but that's okay. 1, 3, 4, 6, 7. I find out what the Y values are. So we got -2, -4, -3. So we'll plug those in. 4, -3. And let's see what the other ones are. 5 and 12. All right. So I got them all plugged in. I'll get rid of that space. So my face is not really in the way, but we can see we got some dots on there. So first thing to do, it says to find a linear model. So we're going to use the linear model. So we're going to do the y1 tilde mx1 plus b. And so we're going to check out what we've got. So we can see over here we've got our parameters and our statistics. So I'm going to screen grab those. There we go. Nice. So now I can just kind of refer to them while I work over here. So what we see is we've got an m, which is the slope, is 2.38596. So remember, we're doing a y equals mx plus b equation. So y equals, again, m right here is 2.38. So let's call that 2.4. We got the x, and then we have to add the b term. So b is over here, so we'll say minus 8.4. And that's it. That's just our linear model. So it looks pretty decent. So we'll move our linear model. We'll move that one down out of the way. And second part for part B says we have to do the quadratic model. So the nice thing is I don't really have to type the data in again. Let me just hide that one. But I do need to put in the code for the quadratic model. So this one's new for this unit, whereas the linear was from a while ago. So y1 tilde ax1 squared plus bx1 plus c. And you'll notice I did use all the capital letters. That's important for Desmos because Desmos will see the little b as a different number than the capital B. If you do them both at the same time and you keep them both either little b's or big B's, then these two numbers are going to be the same and you're not going to get the right answer for the second one. So I kept them all as capitals. And again, I'm just going to screen grab these. You can see the red curve. It looks like it kind of goes through those green dots a little bit better. Since the green dots kind of looked like they went up, then they went down. But again, I'm just going to grab this just so I can refer to it on my notebook over here. So for the quadratic model, again, the nice thing is the code is still just standard form. So we're just going to follow just like we did y and then m and then x and then b. We're going to do the same thing over here. So for the quadratic, y is equal to, and now we got to do a first. So a is going to be 0.87. We'll do x squared. B is going to be next. We got negative 4.67. That'll be an x after it, just because we've got an x after the b. So here we got x squared, x squared. And at the end, we got to do plus c, so 1.88. I took 2 decimals over here, just I wanted to be a little bit more precise. I did 1 decimal over here, just a little bit less precise. And it's important to get a little bit extra precision for the higher order functions. That way they're a little bit better. So next one says, which model will be more appropriate for the data? Justify your choice. Well, visually it looked like the quadratic was a lot better than the linear. And we can go back there and we can check it out. I mean, if we do the linear, like that doesn't even come close to this green dot over here. So even though we could kind of see it, I think the red one's a little bit of a better choice. Now, how can I tell that for sure, though? Because, again, visually, we don't want to say just visually it looks like it. What we want to look at is we want to look at the r squared value. Because remember, the closer that r squared is to 1, the better the fit is. So we talked about looking at the residuals. This is another way to look at the fit that we had talked about. So I'm going to say that the quadratic is better because r squared is 0.9991 for the quadratic, but only 0.7008 for the linear. And we want it to be close to 1. Close to 1 is best. Close to 1 is best. So since that one 0.9991 is closer than 0.7008, that's the one I'm going to pick. So that's what I'm going to go with. If you have a TI calculator, you can do this on the TI calculator. You'll enter in the data again with the stat menu. So before you do anything, you'll do the stat, and then you'll put 1 in, and that'll let you enter in all the data. The X's will go in for L1, the Y's will go in for L2. These are buttons, so let me just make them look like buttons. You press, and then after you have the data in, to do the linear model, you'll hit the stat. Then you have to go over, so you have to go over a menu. And the linear model is number 4. It says linreg. The quadratic model, once you see the linear model, you actually can just hit stat again. You don't have to retype anything in, but you can just hit stat and then over and then 5. And that'll be the quadratic model. And everything should pop back up. Again, if you can't see the R or the R squared, you'll have to turn the diagnostics on. We should take care of that. We should have taken care of that before, because again, once we did that once, it's set for the whole year. But just in case the R's or the R squareds aren't popping up, you have to find that in the catalog is the easiest place to go find it. Since the catalog is in alphabetical order, you press diagnostic on, you just press enter, and then it should work out. But that's what you want to do for number 1. All right, for number 2, we've got a quadratic here. So we've got the function f of x is negative 0.5 times the quantity x plus 2 minus 2. So over here it says first to sketch it. So I guess we can sketch it first. It seems like when we want to sketch it, though, we'll probably take care of a whole bunch of our other things. Because the first question over here says find the axis of symmetry. And the axis of symmetry is always going to be a dashed line wherever our h value is. So here we're at plus 2, so we have to remember to go back 1. So that's going to be the axis of symmetry. I guess I'll just pick purple for this one. Is that x equals negative 2. So when we took this 2 and we switch the sign, that's the axis of symmetry. It's a line, so we want to say x equals negative 2. But we know this parabola is going to fold around that line. So let's see what else we have to do. Identify the vertex. Well, the vertex has to be on this line somewhere. To get the vertex, we're going to go down 4 from the line. So 1, 2, 3, 4. So that's where the vertex is. It's a coordinate point, so negative 2, comma, negative 4. And again, that's either going to be the top or the bottom of the parabola. So for the next part, it asks, does the parabola open up or down? Well, if we look, again, we're doing analysis. We got a negative sign, so we're going to pick open down. It's only because it's negative, so we know we're going down. So we're going to go down from the purple points. So it does say to sketch it. So we want this to be a little bit wider because we have a 0.5, or we can remember that that's like the slope from here. So we'll go down 1 over 2. And we can mirror it. Down 1 and back 2 would also be the same. And with 3 points, we'll get enough points to make the parabola. So again, we can definitely see it's opening down. And then part E says list the domain over which the function is increasing. Well, this function is going up. So if we kind of like track it, we're going to start like way down here. We're going to go up, 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 stop right here, and then we're going to go back down. So if we want to do it visually, which we can do, we'd say it goes up from negative infinity until we get to, we're going for an x value because it says list the domain. So all the way until we get to negative 2. And that's when we stop going up. If it asks for the range, that'd be a little bit different, but we're just going for the domain here. So this is where we're increasing. So we're increasing on the that side, the left half of the parabola, and we're decreasing on the right half of the parabola. So that's where we're increasing versus decreasing. All right. So if you wanted to, and you could plop that into Desmos and check it out, you can plop it in your TI and you can get a visual for it. So if you're a little bit unsure or you just want to double check it, you feel free to graph it in Desmos or your graphing calculator. All right, for number 3, we've got this function. H of x is 5x squared minus 4x minus 10. First, identify the y-intercept. Well, this is in standard form, so the y-intercept's at the end. It's at negative 10. I'll write it as a coordinate point, but you can write negative 10 if you want. Does the parabola open up or down? So again, we want to look here and we see that 5 is positive. Since 5 is positive, we're going to go open up. So we're going to have a regular U-shaped parabola. Next, it says identify the axis of symmetry. Well, we can't find that out just by looking at standard form like we could with the vertex form from the last question. So we got to use the equation negative b over 2a. So remember, in standard form, the first number is a, the second number is b, and the last number is c. So when we plug them in, we get negative sign from the formula. B in this case is negative 4. We got to keep the sign with us. 2 from the formula. And then A is 5. So we'll put a 5 down here. Oh, how did I get to yellow? I don't want the yellow. Yellow doesn't show up very well. 2 times 5. All right, so when we simplify this, this is going to become 4 because the 2 negative signs will cancel out. 2 times 5 is 10, or 2/5. If you want to write it as a decimal it would be 0.4. So either the fraction or the decimal is okay. It's really up to you which one you want. I'm going to stick, I think, with the fraction for right now, but maybe I'll change later. And then part D at the end, it says identify the vertex. So to get the vertex, what we're going to do is we're going to plug either this one or this one. So we're going to plug our answer in for that x and in for that x. So for our vertex, I think we did this in red in class. For the vertex, the y-coordinate is going to be 5. Again, I think I want to go with 2/5. You could put into 0.4 here if you want. I think this is going to be a little bit easier to work with. But if you're using a calculator, it really doesn't matter. You can just put it in as either one. 2/5. And then from the equation we've got minus 10. The reason I think the fraction might be a little bit easier is because 2/5, this squared here, I'm going to cancel out one of the 5s. So it's going to be, what's it going to be? 4. That 5 will cancel out. We'll be left with 1. So 4/5 minus, and then over here, we're going to get 8/5 because 4 times 2 is 5. And since we're working in fifths, I may as well change this minus 10 to minus 50/5, just so that they're all in fifths. Again, if you're doing decimals or if you're going to throw it in the calculator, you don't need to work with the fractions. So my y-coordinate is going to end up with 4 minus 8 is negative 4. Negative 4 minus 50 is negative 54/5. All right, so let's check it out. We get our final coordinate. Don't know why I use blue. We're going to do x-coordinate first, so 2/5. Y-coordinate second, negative 54/5. All right, and again, if you're not sure, you can always double check it. So let's do that. Let's actually see what it looks like. That way we'll verify. That way, in case I did something wrong, it'll get fixed. So we want to do 5x squared minus 4x minus 10. So we'll hide these, hide that. And we get 5x to the 4th minus 4x minus 10. 5x squared, not to the fourth power. Fun function, but not quite. And yeah, 0.4, and then negative 10.8. Negative 10.8 is negative 54 over 5. So that does work out. So again, definitely possible to graph it and solve it graphically if you want, but this is how we can do it algebraically, and it uses our fun equation that we had a lot of times that we used in the unit. So that's how to do number 3. All right, for 4, convert to standard form. So right now it's in vertex form. To convert it to standard form, we basically are just going to expand this right here. So we're going to take this x minus 3 squared, and we're actually going to square it. So x minus 3 squared is x minus 3 times x minus 3. And you can multiply however you wish. This is kind of like a review question from last unit. I'm going to multiply with the boxes. But if you want to do the double distributive property with the arrows, you're more than welcome to. 3x, 3x, and 9. So x squared minus 6x plus 9. Now all that is that's just this parentheses part expanded. So right now it's going to look like y equals 2 x squared minus 6x plus 9, because that's what this parentheses part is equivalent to, and then still plus 10. So I'm not quite done because I still have those parentheses. I got to get rid of the parentheses. So I'm going to distribute to get y equals 2x squared minus 12x plus 18 plus 10. One final step, we could combine the like terms. Y equals 2x squared minus 12x plus 28. So we can get the vertex pretty quickly here. We know the y-intercept now is 28. And it's kind of cool because the 2 stays out front because it's still going to be twice as narrow. So that's kind of interesting. All right, for number 5, write the transform that results of f of x equals x squared that results from a vertical reflection, horizontal translation of 5 right, vertical translation of 2, and a vertical stretch by a factor of 6. So for this, we need to remember the equation. Y equals, since we're doing all the motions, we probably want it in vertex form. A x minus h squared plus k. And so our goal is basically to fill in all those letters, find out what is A, what is H, and what is K. So let's just kind of go in order that they give it to us in the problem. So first we have a vertical reflection. So a vertical reflection means I need a negative sign in front of A. So let's build it up. Let's put a negative sign in front of whatever our function is going to be. All right, next thing we've got is we've got a horizontal translation. So horizontal goes with the H. That's kind of cool that it's named H, but it's with the X's. We know the X's go left and right, so we know the horizontal translation is going to be blue. We're going 5 to the right. So if we're going to the right, we would think we'd want to add, but remember, 5 to the right is like a normal 5 for H. So we're just going to put a 5 in for H because we're going 5 to the right. So the negative sign's already in the formula, so we're good to go because we want x minus 5. And remember, that makes sense because inside the parentheses, since we got a negative, we're going to move to the right. Next, we got a vertical translation of up to. So again, vertical translation is going to go with k. Underline horizontal. So that's just the number on the end. So up to would be a plus 2. If it was down, we'd make it a negative 2. We still have this vertical stretch by a factor of 6. So a stretch means we're going to get a little bit thinner. So we want a positive number, not a positive number, we want a number that's greater than 1. The negative's fine. The negative just stays out front. So we get y equals negative 6x times the quantity x minus 5 squared plus 2. And that's it for number 5. For 6, complete the table. Is the model a good fit for the data y? So just to show you there's nothing really behind me. Nothing really behind me in those boxes. So we're given the actual and the predicted and the residual. So we have to kind of fill it in. So we need the residual formula. So for the residual formula, the residual is the actual minus the predicted. Well, actual's right here and predicted's right here. So our goal is just we want to subtract from one column to the next. So 102 minus 99 is 3. 120 minus 110 is 10. Now here we got to think. 133 minus something is negative 1. So we could set up an equation. So if you wanted to do it with an equation, we could do 133 minus x equals negative 1. Subtract 133 from both sides. Negative x equals negative 134. Divide both sides, not by x. Divide both sides by negative 1. And get x equals 134. So we could choose to do it that way. You could also just visually look at it, and if you can logically find that it's 134, that's totally fine. So we're going to logically think about the last one, because remember, the residual is how far away we are. So if our predicted sales, if our actual sales were 3 less than the predicted sales, this should be 145. And we can double check. 145 minus 148 is negative 3, so that does work out. So we got that part down. We got everything in the table. So we just use the residual formula. Second part of the question says, is the model a good fit and why? So remember, we want to look at the residuals and we want to look for a pattern. So is there a pattern to these numbers? I would say no. I mean, it goes up and then it goes down, but not really in any meaningful way. Like we got a couple positives, we got a couple negatives. So I'm thinking that this is going to be no pattern. So I think it might be a good fit. If you think that there is a pattern there, you should explain the pattern, because that's part of explaining why. You can't just say pattern, because I don't know what the pattern is. So either they're all positive, they're all negative, always going up, always going down are common patterns. This one I really wouldn't consider this a pattern, because again, we do go up and then we go down. With 4 data points, it's a little hard to see if there's going to be one or not, but I would say no pattern on this one. All right, so for 7, what type of model does this data represent? So here we're choosing between linear, quadratic, or exponential. So there's only 3 choices. So we said we could check the differences first. Because if the differences are all the same, it's an arithmetic sequence, which means it's got to be linear. So we have to do some subtraction. So we're going to do negative 39 minus negative 22. So that's going to be 17. Not negative 17, just regular 17. That is negative 17. All right, then we got to do negative 22 minus negative 9. So if we do that, we're going to get negative 14. Negative 13. We're working on it. All right, then we got to do negative 9 minus 0. Well, that's a good one. Okay, that's negative 9. Not going to mess that one up. And then 0 minus 5. So 0 minus 5 is negative 5. So if the differences are the same, then it's linear. But these numbers are not the same, so it's not linear. Okay, well, the next thing to check is the second differences. If these are the same, then it's going to be quadratic. All right, well, let's check it. So if I subtract these, 17 minus negative 13 is negative 4. Negative 13 minus negative 9, that's negative 4. Negative 9 minus negative 5, that's negative 4. So these are the same, so we're going to go with quadratic. So the last choice that we could have picked is we could have picked exponential. Remember, exponential is the one where you could multiply by the same thing every time or divide by the same thing every time. Or if neither of these works, probably going to be exponential. But just so you know what the test is, it would be something to multiply. So some pattern like 1, 2, 4, 8, 16, 32, where we're multiplying by 2 every time, that would be a good exponential one because we're multiplying by the same number every time. All right, next, this looks pretty familiar from when we did the modeling. So Kelly wants us around a 14-foot by 22-foot pool by a deck that's X feet wide. So let's draw the situation out. So 22, 14, these are in feet. So that's our pool. Some waves in the pool. And then we want to make a deck. So we want to surround it with a deck that's X feet wide. Well, let's use this for the deck. So there's our deck, and it's going to be X feet wide. So we're going to have X on that side, X on that side, X on that side, and X on this side. So what we want to do is find the area of the pool in the deck. Area is going to be length times width. So the length, if we check, we've got 1x, we've got 2x, and we've got 22. So our whole length is going to be 2x plus 22 feet. So we have 22 feet from the pool, and there's two sides of the deck, so we have two x's. I don't know why I put feet there. We don't want feet right there. 2x plus 22. For the width, we'll check the up and down. So we've got 14 from the pool, but then there's also x and another x, because again, there's deck on both sides of the width of the pool. So this is going to be 14, well, 2x plus 14. So that's our area, so that's what we wanted to answer for part A. Now for part B, it says convert the area to standard form. Well, again, just kind of like we did in one of the previous problems, this is going to be kind of a review from the last unit. So we're going to multiply these. Actually, why don't I do it the other way? Since I did the boxes with the last one, we'll do that. We'll do the arrows with this one. But you could use the boxes if you wanted to. So for this one, this is where we say we've got 2x, and we want to take the big piece. So 2x times 2x plus 14. And with the second piece, we got the 22. We still want to use the big piece again. So 2x plus 14. And so with the double distributive method, we're going to distribute the 2x to both parts. And that'll give me 4x squared plus 28x. We want to distribute the red 22 to both parts. So that's going to be 44x and 22 times 14. So we got 2 times 4 is 8. 8 again, 0, 22. 803. So we get plus 308. Last step when we use the double distributive method is to try and check for like terms. We do have two like terms right here. So we'll finish with 4x squared. So this is about 30, so that's going to be 72x, and then plus 308. And now we're in standard form. Again, the first thing is the squared term, the second is the x's, and the last is the number, the 308. So just make sure that the x squareds are first, and then the numbers at the end, and then you should be okay with standard form. Sometimes when you multiply, things get a little bit jumbled up, but we do want it in standard form, so we have to go x squareds first, then the x's, and then just the regular number. So that's what we get for number 8. All right, so I think we're at the end. Yeah, number 9 is the last question. So it says a grasshopper jumped with an initial velocity of 25 feet per second from a leaf 1.5 feet high to the ground. Write an equation that models the grasshopper's path. So looks like we're doing the vertical motion model. So we had to remember what that is. Again, it's basically standard form, but we've got h of t is equal to negative 16t squared plus v naught t plus h naught. Okay, so that's our vertical motion model. We just need to fill in just the red and the blue, and then we'll be done with part A. So we get h of t is equal to negative 16t squared plus, all right, well, v naught is the initial velocity. So initial velocity is 25 feet per second. So plus 25t. And then we're going to go from the leaf that's 1.5 feet high all the way to the ground. So we're going to go plus 1.5 because we're starting on the leaf. We're going to end on the ground. And that's it. So that's our vertical motion model. So we're done with the first part. All right, second part says, what's the grasshopper's maximum height? Well, since this is a word problem, I mean, we could use the same formula. We could do the negative b plus or minus, we could use negative b over 2a. That'll give us the x value for the vertex, and we could plug it back in. But since this is a real world problem, we want to end up with decimals anyway. We did the other one with fractions because it was kind of a pure math problem. So I think the goal right here is I'm just going to graph this. I'm going to grab the maximum height from the graph. I don't think I need to use the equation in this one. If I do it, I don't want to type h of t. I could if I wanted to. I'm actually going to put in negative 16x squared, because Desmos likes x instead of t, plus 25, 5 and 1.5. 25x 1.5. And that gives me my equation for my grasshopper. Now, apparently I have a super grasshopper because my grasshopper goes all the way up here before ending down after 1.62 seconds. We're starting at the leaf is at 1.5. So this grasshopper has some big jumps because it goes all the way up to 11.266. So like 11.3. So I'm going to say that that's my maximum height is 11.3 feet. So I don't know what kind of grasshopper this is, but it got up to 11.3 feet. And so that's what we're going to put down, 11.3 feet. So we want to make sure we're all good with our feet. And that's going to be it. So that's everything on the review guide.